The Earth, our spaceship. Welcome aboard for our one-year cruise around the sun. Yes, we do revolve around the sun, but not on a circle, on an ellipse. And it's now, during the first days of January, that we're closest to the sun. So why is the weather so cold? In fact, the difference between near the sun and far from the sun is insignificant. There's a much more important reason. The Earth doesn't spin straight, but slightly askew. The axis isn't vertical, it's tilted on its orbit. So when the northern hemisphere tips into shadow, the nights are long, the days are short. But more importantly, because the Earth is tilted, the sun's rays reach us at different angles. In the tropics, a ray of sunlight hits the ground vertically. It's hot. But the same ray in the northern hemisphere arrives at an angle. Its energy is spread over a surface 3 times greater, providing 3 times less heat. We're cold. In the north, it's winter. In the south, it's summer. The tilt of the Earth's axis gives us the seasons. At this very moment, you're hurtling through space at 107,000 kilometers an hour. That's 30 kilometers every second. The Earth takes a year to go around the sun. And along with the Earth, 8 other planets circle the sun, each on its own orbit. On the orbit just next to ours is our neighbor, Venus. Venus travels faster than the Earth, overtaking us. It's the brightest planet, the one we see best. Sometimes in the evening, sometimes in the morning. Why in the morning? We see Venus to the right of the sun. Seen from the Earth, this is what happens in the morning. We are looking at the part of the sky where Venus is. It appears on the horizon well before the sun, while it's still dark and the sun is still below the horizon to the left. That's why, in this position, we see Venus in the morning, at dawn. As the Earth continues to turn, we see the sun. It lights up the sky until we can't see the stars or planets anymore. So we continue our voyage on board our planet Earth. On the next orbit to the left, the Earth has a faster-moving neighbor, traveling at 125,000 kilometers per hour and overtaking us. This is Venus. We call it the morning star, but it's not a star, it's a planet. What's the difference between a planet and a star? They look the same. But the stars shine like our sun. The planets don't shine, they reflect the sun's light. They're part of our solar system and are near to us. The stars are very far away. We can't reach them. This is Sirius, next to Orion, one of the closest stars. Even such a close star is out of our reach. If our spaceship Earth left its orbit and headed out of the solar system towards Sirius at its normal cruising speed, we'd take 80,000 years to get there. While at the same pace, we'd reach Venus in just 16 days. 80,000 years for Sirius, 16 days for Venus. That's the difference between the far-off universe of stars and our solar system with its nearby planets. Our cruising speed is 107,000 kilometers an hour. That's 30 kilometers every second. But remember, we're not traveling in a finely stabilized spaceship. This is a giant merry-go-round. We all know that the Earth turns on its axis, but how can we tell? When we look at the sky, we see the sun rising in the morning, climbing into the sky at noon, and setting in the evening. Then at night we see the moon and the stars doing much the same thing. But if we look at the Earth from space, we see that half of it is always lit by the sun, while the other half is in darkness. This is what we call day and night. Our field of vision turns with the Earth. In the day, we see the part of the sky where the sun appears. At night, we see the part of the sky which isn't exposed to the sun's rays. So we can see the stars and the planets. In fact, when you look at the sun, it seems to cross the sky, while in reality, it's motionless. It's just that you're seeing it from a revolving merry-go-round. Tonight, you'll see the moon, the stars and the planets rise, glide across the sky and set. But it's really the Earth which is turning as it hurtles through space. On the 20th of March at the equinox point, we'll be here, and spring will begin. But these pictures don't show the true proportions of the Earth and Sun. Compared to the Earth, the Sun is very, very big. Imagine a sun the size of a great cathedral. On the same scale, our Earth is just a soccer ball rolling 5 kilometers away on the edge of town. Still, on the same scale, Jupiter, the greatest of the planets, is the size of a car, driving along 30 kilometers from the city. And on the same level, Pluto, the most distant planet, is a mere tennis ball, moving on an orbit 200 kilometers away. A cousin so distant, we might wonder if it's still part of the solar system family. A family completely dwarfed by its colossal sun. All the planets, Earth included, represent only 1,000th of its mass. What we call the solar system turns out to be the sun and a few pebbles. The Earth is one of these pebbles. It takes 365 days, 12 months to go around the sun. The closer a planet is to the sun, the faster it moves. Venus is closer to the sun than we are. The brightest of the planets, it's easily visible, sometimes in the evening, sometimes in the morning. It completes its orbit in less than 8 months. Even closer to the sun, Mercury completes its orbit in less than 3 months. You'll find it hard to see Mercury. It's too near the sun. Mercury, Venus, and then the third stone from the sun, us. Next, still farther from the sun, the planet Mars moves slower than we do, taking 2 years to make its way around. Much more distant than Mars, Jupiter, the biggest planet, takes 12 years to complete its orbit. Even farther away and slower still is Saturn. 30 years for a single orbit. Beyond Saturn are Uranus, Neptune, and Pluto, which takes 248 years to go around the sun. In our family of planets, 4 are visible among the distant stars: Saturn, Jupiter, Mars, and Venus. To help you get your bearings during this year-long voyage, here's a frame of reference: the zodiac. The zodiac is an imaginary band where groups of stars are set out, constellations marking the different sectors of this vast backdrop. The constellations of Capricorn, Aquarius, Pisces, Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpio, and Sagittarius. Today, the Earth is here. The Sun is in line with the constellation of Sagittarius. The Sun is in Sagittarius. After a few weeks, when the Earth has continued on its orbit, the Sun will be in line with the constellation of Capricorn. The Sun will be in Capricorn. At night, you can locate the planets using the constellations of the zodiac. Saturn sometimes appears in line with the constellation of Pisces, and Mars in line with Virgo. The Sun in Sagittarius in January, In the horoscope, it says Capricorn. If you're born a Capricorn, it means that the sun was in Capricorn on that day, doesn't it? We mustn't confuse the constellations with the astrological signs, based on the zodiac as it was 2,000 years ago. Since then, everything has moved on like this. Because over the millennia, the Earth's axis slowly swings and changes the angle of the constellations. The sun's light takes 8 minutes to reach us. The sun and the planets are very close to us. This is our neighborhood. But for the light that reaches us from the stars, it's quite a different story. You recognize the Great Bear, Big Dipper, when you look north. The Great Bear is made up of 7 stars. Imagine we're looking at the Great Bear, not from Earth, but from another part of the universe. Here we see that its 7 stars lie at very different distances. The light which reaches us today left these stars in different centuries, showing us the image of a star as it was in our grandfather's day, the image of another as it was in the age of Charlemagne. These images dating from different centuries are superimposed to form our view of the Great Bear. The light which shows us the image of the Andromeda spiral today left that galaxy more than 2 million years ago, at a time when even cavemen hadn't yet appeared. Stars, galaxies, and all these very distant objects are images from different ages. You travel back in time when you see them. But when you look at the planets, you see them now, live. In the solar system, we travel in the present. When we look at the stars, we see the past. Throughout this voyage, we're accompanied by our satellite, the Moon. There it is on your screen and, at the same time, outside your window. Your screen is a porthole on the Spaceship Earth. The Moon takes nearly a month to circle the Earth. Seen from the Earth, the Moon seems to follow roughly the same path as the Sun. It rises in the east and sets in the west, like the Sun. But the Sun rises in the morning and sets in the evening because the Earth is turning, while the Sun remains firmly set in the center of the solar system. So every day towards noon, we see the Sun in the same part of the sky, to the south. Things are different with the Moon. The Moon revolves slowly around the Earth, and each day it changes position. Tomorrow at the same time, you won't see it in the same place as today. It will be 2 hands' breadths to the left. As it progresses on its orbit, the Moon lines up with distant planets, allowing us to locate them in the sky. Saturn, for example, at the other end of the solar system. Here's the Moon, and here a hand's breadth to the left is Saturn. If you take your bearings from Saturn, you can measure the daily displacement of the Moon. One evening, the Moon is to the right of Saturn. The next day, it will have moved to the left of Saturn. Each night, the Moon appears to have moved 2 hands left. And each night, the Moon passes by 50 minutes later than the night before. 50 minutes is the time the Moon takes to travel the width of 2 hands. That is, to appear where it was yesterday at the same time. Every evening, the Moon is different. It never stops changing. One day it's a small crescent, the next a slightly thicker crescent. A day later, it's even thicker. But why a crescent? In space, 1/2 of the Moon is always lit by the Sun. But from the Earth, we see the Moon in another perspective. For us, it edges a little farther from the Sun each day. When the Moon has moved to a position only slightly away from our view of the Sun, it appears only backlit, and we can only see a tiny part of its sunlit half, a crescent. The Sun has just set. It's there on the right, just below the horizon, and from there, it lights up the Moon. The crescent is still aimed towards the sun, of course, as it's the sun which lights it. Each day, the moon moves a little farther from the sun. So each day from the Earth, we see a larger part of its lit half. A crescent which grows daily and which will become a half moon. In its half-moon phase, the moon overflies our orbit. It crosses the path the Earth has just taken. Every day, the Earth turns once. During this day, the moon continues on its way, so we see it displaced to the left. It will reach yesterday's angle 50 minutes later. In crossing the Earth's orbit, the half-moon becomes a reference point which allows us to picture our own path. Normally, we can't really see where the Earth is going. But on the night of the half-moon, we can see where we've come from. Where you see the half-moon, that's where the Earth was 4 hours before. Look at your watch and look at the half-moon. Up there, at that point in the sky, is where you were 4 hours ago. And in 4 hours, the half-moon will have taken your place. It will be there where you're standing now. For once, as you look at the half-moon, you can imagine the invisible track that carries us once around the sun every year. As the moon moves on farther and farther, passing 50 minutes later every night, it finally appears not only at night, but also during the day. When it enters the second quarter of its orbit, it becomes so bright that it can be seen by day, in the afternoon in the southeast. Where does the moon come from? We don't really know. Perhaps in the beginning, when the primitive Earth was not yet compact enough and was spinning very, very fast, part of it came away and began to revolve around the Earth. But perhaps the moon came from a distant part of the solar system, passing too close to the Earth. It may have been captured by its pull and dragged into its orbit. Finally, there may have been a collision with an asteroid, with the debris condensing to form the moon we have today. A moon which accompanies us throughout our voyage around the sun. As we see the moon shift every evening, we can imagine its path around the Earth. We can imagine the space in which the moon moves around the Earth. And when the moon is 50 minutes late, there's a shift in time. So the same thing is happening in both space and time. During our journey, we'll see that space and time are very close cousins. We're here, hurtling along on our orbit at 107,000 kilometers per hour. In 2 months, we'll be here at the vernal point, meaning the point of spring. A point in space or a point in time? The closest planet to the Sun is Mercury. Mercury is hardly any larger than our Moon. On its close orbit, Mercury zips around the Sun in less than 3 months. When Mercury appears close to the Sun, this is what we see from the Earth. As soon as Mercury appears on the horizon, the sun rises almost simultaneously and lights the atmosphere. Mercury immediately disappears in the blue sky. When Mercury appears furthest from the sun, it's an hour and a half ahead of the sunrise. Now's your chance. If the eastern horizon is clear with no mist, you can catch a glimpse of Mercury before the sun comes up. But Mercury moves very fast in its orbit. 1 week later, it will be swallowed again by the sun's glare. And we'll have to wait for 4 months before it's once more in a position where we can see it. It takes 3 months for Mercury to travel around the sun and reach this point. During these 3 months, the Earth will have covered a quarter of its orbit. Mercury will take another month to overtake us and reach this point where we can watch for it early in the morning. Mercury, gripped strongly by the nearby sun, has no moon. Neither does Venus. Earth, the third planet, has one moon, of course. Mars has 2 satellites, Deimos and Phoebus. Phoebus was knocked about in a cosmic collision. Further from the sun, Jupiter is surrounded by 16 satellites. You can see the 4 largest with a pair of binoculars: Ganymede, Callisto, Io, and Europa. Further away still, Saturn has a wide array of satellites, large and small, neighboring its spectacular rings. The Earth has only the moon as a satellite. The moon shows us one side, always the same. So, if we always see the same side, why all these different crescents from night to night? The side of the moon which always faces Earth is lit by the sun differently from day to day. Just after the new moon, it's practically backlit. When we see the half moon, the moon is lit from one side. Now the moon moves through the second quarter of its orbit, facing the sun more and more directly, and showing us an ever-growing portion of its sunlit half. It's now almost the full moon. On the eve of the full moon, at sunset, the moon is just above the horizon. Then, as it continues its journey around the Earth, it lines up with the Earth and sun, facing the sun. Now it rises just as the sun sets. It catches the sun's rays full on. On the night of the full moon, it reflects the most light towards the Earth. Whether crescent or full, the moon always turns the same side towards us. This isn't so for the Earth and sun. As the Earth rotates every 24 hours, it turns all sides to the sun. Seen from the sun, the Earth has no hidden side. The moon is linked to the Earth, whose mass is much greater. In the Earth-Moon pairing, it's the Earth's pull which prevents the moon from spinning freely. Its movement slowed, it always shows us the same face. The same thing happens to little Mercury. The enormous sun prevents Mercury from turning freely. In space, between neighbors, it's mass that rules. If you look at the full moon in winter, you'll see that it rises very high in the sky, while the sun, as always in winter, stays quite low. Why this difference? It has nothing to do with the moon. It's our movement, the movement of the Earth, which changes everything. Seen by an extraterrestrial, the moon is lined up with the sun, more or less on the same plane as the Earth and planets. For us on Earth, our frame of reference is the zodiac. Against this backdrop, we locate the stars, the planets, and also the sun and moon. The Earth is tilted in relation to the zodiac, so during the day, the sun appears low on the horizon. At night, we look in this direction, and now the moon appears high in the sky. During the day, like this. At night, like this. The Earth rotates at an angle. Seen from the Earth, it's the zodiac that tilts and seems to undulate. At noon, the sun passes low on the horizon. At midnight, the moon passes high in the sky. But the zodiac's undulation is simply the effect of the Earth's movement. As it circles the Earth in 1 month, the moon seems to pass close to each planet. During these conjunctions, the moon allows us to locate these planets and help us to situate our solar system better. Sometimes the moon, the Earth's nearest neighbor, can help us locate Saturn at the other end of the solar system. In 2 weeks, the moon completes half its journey around the Earth and lines up with Mars. On nights of conjunction, you can see Mars, a little more yellow than the stars, just next to the moon. But remember, the moon, Mars, and the stars aren't really neighbors. The moon is very near. Moonlight reaches us in 1 second. The light reflected by Mars takes 8 minutes to arrive on Earth. The star just to the right of Mars is so far away that its light was emitted over 400 years ago in the days of Shakespeare. The stars are very distant and inaccessible. The planets are close to us. We are the first generation to have the solar system within our reach. Seen from the Earth, everything seems to revolve around us. The sun, the moon, the planets, and stars. This explains the view of the universe in ancient times. Earth in the center, under the vault of heaven, with the sun, moon, and stars fixed to this vault. There was a problem with planets like Mars which moved backwards and turned in strange loops. This was hard to explain if the Earth was at the center of the universe. But then, Nicholas Copernicus had a stroke of genius. It wasn't the Earth that was set motionless at the center of the universe, but the sun, and the Earth became a planet moving around the sun with the other planets. This discovery changed our perception of the universe. And the Earth found its true place. Today, when we travel together on Spaceship Earth, discovering how the solar system works, spare a thought for Copernicus. It's partly thanks to him. Why does the Earth turn? Any mass which receives a blow or any kind of impact off-center begins to turn. This has been happening to matter constantly since the Big Bang, the original explosion billions of years ago. So everything turns. In the infinitely small, electrons spin around the atomic nucleus. In the infinitely large, galaxies turn. Nebulae made up of gas and dust rotate and contract. with the great mass in the center, the sun. The rest, still turning, condenses into planets. One of these planets, still rotating, is the Earth. And you can actually see it turning. The shadow of a house which moves during the day, or the rays of the sun coming through the window and gliding slowly across the floor. Just look at these things, anytime, anywhere. We can see the Earth rotating. The rotation of our Earth is rapid or slow, depending on where we are. Each of these 3 circles makes a complete turn in 24 hours. Naturally, it's the largest circle which travels the greatest distance. So it's here, on the equator, that the Earth rotates fastest, 1,600 kilometers per hour. That's why rockets are launched from here in Kourou, French Guiana, and from Cape Canaveral in the southern United States. To escape the Earth's pull, very high speeds are needed, so the additional rotation speed adds to the thrust of the rockets, a very useful boost. A few miles from the North Pole, very close to the axis, the Earth moves at only 3 kilometers an hour. You can walk at the speed of the Earth's spin. And here, between Scotland and Canada, the Earth turns at roughly 900 kilometers an hour. That's the speed of the planes we take to travel from Europe to America. An extraterrestrial watching from a distance could see our plane taking off in Paris, then remaining almost motionless while the Earth turns below. Finally, when New York slides under the plane, it lands. We arrive in local time at almost the same time we left. For the passenger flying from Paris to New York at the speed of the Earth's rotation, time stops. And for the person who stays quietly at home but wants to call his friend in New York, at noon he runs the risk of waking him up because in New York it's only 6 o'clock in the morning. Why? The Earth turns. Every hour it points a new segment, a new meridian at the sun. On the meridian facing the sun, it's noon. Paris, New York is a quarter of the Earth. Quarter of the complete turn the Earth makes in 24 hours. And a quarter of 24 hours is 6 hours. Paris, New York, 6 hours difference. In Paris, the sun is above the meridian. It's also visible in New York, where it's just rising over the horizon. And at the same time, in Tokyo, it's setting. In 6 hours, when the Earth has made a quarter turn and the New York meridian is pointing at the sun, it will be noon in New York, and 6 p.m. in Paris, where we'll see the sun setting on the horizon. Each minute, another city, another country turns to face the sun. Each city, each country has a different local time. With the appearance of the telegraph and the telephone, a universal system was needed, and the Earth was divided into 24 time zones. Paris, New York, 6 hours difference. Is that a distance in space or in time? Probably both. We fly as fast as the Earth turns, and our space probes catch up with Jupiter and Saturn on their orbits. Our human dimensions have become planetary dimensions. The solar system is within our grasp. We're on our way to this point that marks the beginning of spring. The planets accompany us around the sun, but at different speeds. We can see only the ones that are well out of the sun's way. Mercury and Venus are often hidden by the sun's glare, and so is Jupiter far away on the other side of the solar system. Looking from the Earth, when Jupiter is lined up with the sun, we can't see it. However, when Saturn, at the bottom of the screen on the left, is at an angle well clear of the sun, we can see it all night. The same goes for Mars, the red planet, in opposition here facing the sun. Looking from the Earth, we can use the backdrop of the zodiac to get our bearing. The zodiac is an imaginary band holding groups of stars or constellations visible in the distance behind the planets. Planets remain invisible when they pass in front of the same constellation of the zodiac as the Sun. Here in Capricorn. During the day, we can't see them because they're too near the Sun. And when the Sun sinks below the horizon, well, they disappear under the horizon too. At night, planets at a wide angle to the Sun are very visible. The Earth continues on its way, and the Sun seems to move across the zodiac. It passes from Capricorn into the constellation of Aquarius. On the right, Mars, the red planet, moves more slowly than the Earth. Every 2 years we catch up and overtake it. On the left is Venus, traveling faster than us. Mercury, the nearest planet to the Sun, moves twice as fast as Mars. The closer a planet is to the Sun, the faster it revolves around it. A long way from the Sun, the outer planets travel slowly around their orbits: Jupiter, Saturn, Uranus, Neptune, and Pluto. 400 years ago, when the telescope hadn't yet been invented, a Danish astronomer, Tycho Brahe, measured the transit of the planets. Tycho Brahe set up a large panel, and night after night he recorded the hour and minute when the stars and planets passed behind his panel. In the Middle Ages, the Earth was thought to be at the center of the universe. Then Nicholas Copernicus had a stroke of genius. The Earth isn't at the center of the universe. The Earth and the planets revolve around the Sun. Tycho didn't believe him, but fortunately, he showed his records to Johannes Kepler. Their meeting changed the world. Kepler knew Copernicus's theory, and using Tycho's measurements, he was able to work out the movements of the planets. The planets do revolve around the Sun, but in elliptical orbits. The Earth and the planets move faster when they're near the Sun, and more slowly when they're far away. It takes the same time to cover the long distance on the left as the short distance on the right. The short, wide slice is equal to the long, narrow slice. Kepler's discovery helped us choose the right path to travel to the Moon and Jupiter. Our calendar also depends on Kepler's laws and the variable speed of the Earth. The nearer we are to the Sun, the faster we travel. This changes the timetable of our journey around the Sun. Now we're slightly nearer the Sun. The Earth accelerates and gains a little ground. But in the summer, further from the Sun, the Earth slows and drops back. The spring equinox is on the 20th of March, and the autumn equinox on the 23rd of September. The Earth reaches the autumn equinox 7 days late. To cover this summer half of its orbit, the Earth takes 7 days more than it does to cover the same distance in this winter half. So Kepler's law is no abstract notion for astronomers. It directly affects our calendars. At the moment, we're here, ahead of schedule. Roughly every 2 years, Mars doesn't follow the movement of the other planets. It begins to move backwards. Normally, Mars moves forward against the backdrop of the zodiac. We can see Mars moving in front of the constellations of Gemini, Cancer, and Leo, and heading towards Virgo. But here, instead of moving in line with Virgo, Mars returns towards the constellation of Leo. In the days when men thought the Earth was at the center of the universe, they'd already noticed the loops made by Mars and constructed complicated theories, but they failed to explain this reverse motion. Nicholas Copernicus's theory explained everything in the simplest way. The Earth revolves around the Sun like Mars, but the Earth travels faster than Mars and overtakes it. When it does so, Mars seems to move backwards against this backdrop of stars. After 2 months, Mars returns to its usual motion, which has really never changed. After 2 years and 2 trips around the Sun, we meet up with Mars again and overtake it. Little by little, the Earth catches up with Mars. When it begins to overtake the red planet, Mars shifts into reverse in relation to the stars of the zodiac. Then overtaken, Mars moves forward again. Thanks to Copernicus's discovery, Mars revolves around the Sun with no loops. Each month, when the Moon revolves around the Earth, it lines up with the Sun. This is the new Moon. The new Moon brings us tides. The water in the oceans is pulled by the Moon to form a high tide bulge on the lunar side. Each day, the Moon passes 50 minutes later than the day before. That's why the tides happen 50 minutes later each day. When the Moon lines up with the Sun, they pull together, drawing the water in the same direction. This is the spring tide. But why are there 2 tides a day when the Moon only passes once? The Earth's center of gravity isn't in the same place as the center of gravity of the Earth-Moon pairing. The first tide on the lunar side is caused by the pull of the Moon. At the same time, on the other side of the Earth, there's a second tide caused by centrifugal forces. What's more, the Moon's orbit is an ellipse. Sometimes the Moon is near, sometimes it's farther away. The nearer it is, the stronger the tide. And when the Moon's closest approach to the Earth coincides with the new Moon, it gives us the strongest tides of the year, sometimes even stronger than the equinox tides. Now we're here. We'll reach the spring equinox in 5 weeks. So why is the Earth round? It's a question of mass. The Earth's mass exerts such a pull that every part of it is drawn towards the center. But this doesn't work for asteroids. Asteroids are tiny planets, so small there's not enough force to pull together all their matter and form a sphere. On the Earth, which has a huge mass, the pull towards the Earth's center is irresistible and nothing can escape it. Fortunately for us, since this pull keeps the atmosphere, the air we breathe, around the Earth. It's the Earth's mass that gives us our weight, keeping our feet firmly on the ground and preventing our Australian friends from falling off into space. You feel this pull each time you have to climb the stairs. Whenever you try to move away from the center of the Earth, you have to overcome the Earth's pull. And when something slips from your hands, it's immediately caught by the Earth's pull and falls. They say this is how the Earth's pull was discovered in the 18th century. An apple fell on Isaac Newton's head, making him wonder, why? Because the enormous mass of the Earth attracts the small mass of the apple. So why doesn't the Moon fall onto the Earth? And the Earth into the Sun? The force of attraction isn't the only force acting on the Earth and the planets. Formed from this matter soup, the planets were subjected to a strong centrifugal push away from the center. Balancing these centrifugal forces and the pull of the Sun, each planet finds its own orbit. The pull is strongest near the Sun. The force of attraction is greatest for Mercury, just next to the Sun. To remain in orbit, it has to move fast, 170,000 kilometers an hour, while the Earth only travels at 107,000 kilometers an hour. The Earth is further from the Sun, and the Sun's pull is weaker, so on our orbit, a slower speed is enough. Even so, this slower speed is 30 kilometers every second. Imagine traveling somewhere 30 kilometers away in 1 second. At the moment, we're getting 3 extra minutes of sunlight every day. Why? The Earth revolves around the sun, but the Earth's axis always points in the same direction. Our planet never loses its bearing. At the moment, the South Pole is in daylight, while the North Pole remains in darkness throughout its winter. But during our circular journey, the North Pole gradually leans towards the sun. So here, the sun, which seemed to travel on this path yesterday, rises more to the left today. At noon, it rises higher, and in the evening, it sets further to the right. Look for a marker when the sun rises and sets, and tomorrow you'll see it rises more to the left, is higher at midday, and sets further to the right. If your windows more or less face south in the winter, the sun, which is low in the sky, shines on the wall facing the window, but gradually the sun, which climbs higher in the sky every day, will shine on the floor in the middle of the room. And in the summer, when it rises highest in the sky, it will only shine on the floor just next to the window. Now in winter, the sun's rays reach the far end of the room. Look at these rays and imagine the position of the Earth in the solar system. Imagine your place in the universe. As the Earth orbits around the sun, its axis always remains tilted in the same direction. So the axis is a useful reference for measuring time and finding out what time it is. We can imagine the axis of the Earth jutting from the North Pole like a rod. And if we draw a dial on the ice, the shadow of the Earth's axis gives us the time. But there's no need to travel to the North Pole. We can make miniature models of the Earth's axis. These are sundials. At the North Pole, the rod which prolongs the Earth's axis will be straight, at a right angle, 90 degrees. In Stockholm, at a latitude of 60 degrees north, to be parallel with the Earth's axis, the rod must be tilted 60 degrees. A little further south in London, 51 degrees. In the Philippines, 15 degrees. And at the equator, the rod would have to lie flat on the ground. The ground is parallel with the Earth's north-south axis. No more shadow, no more sundial. But there are other types of sundials, all aligned with the north-south axis of the Earth. Although you don't feel the Earth's rotation, you can see it, not only in sundials, but all around you. Every house and every tree throws a shadow. You just have to look. As you follow the shadows, you'll almost feel the Earth's rotation. In the solar system, we're well acquainted with our neighbors, the planets, their position, speed, and movement. But comets come as a surprise. They're the ones we know, like Halley's Comet, which passes regularly every 76 years. But sometimes new comets appear, like Hale-Bopp in 1997. Comets are smaller than planets. They move in elliptical orbits. Some come from distant regions of the solar system, pass close by the sun, then head off again. As they approach the sun, they throw off enormous quantities of gas and dust. These substances form the tail of the comet, which stretches out in the sky like hair in the wind. Comet means hairy in Greek. The comets are little hairy planets. We tend to believe that when comets race through the sky, their body is in front and their tail behind. In fact, the tail always faces away from the sun, since it's the stream of particles flowing from the sun, the solar wind, that blows the comet's tail outwards. Without their tail stretching into space, comets would be invisible. Remember, this is real, and it's happening right now. At this very moment, you're hurtling through space at 107,000 kilometers an hour. That's 30 kilometers every second. Today, we're here. In 4 weeks, we'll be at the equinox. Here, the beginning of spring. During our trip through the solar system, we are escorted by our neighbors, the planets. This week, let's look beyond the planets to the stars. They're infinitely further away, but we can still use them as guides. One star always tells us which way is north. Polaris, the pole star, easy to find, 5 widths behind the Great Bear, Big Dipper. The pole star is aligned with the Earth's axis. All night, the stars seem to whirl around the pole star as it remains motionless, naturally since it's in line with our axis of rotation. So the pole star is a practical and reliable landmark. Christopher Columbus used it when unknown lands. He decided to cross the ocean on the 28th parallel. Every night, he measured the angle of Polaris. As long as his quadrant showed 28 degrees, he knew he was on course. He hadn't drifted south or north. He was following the 28th parallel. Do what Christopher Columbus did. No telescope, no mathematics. Just look at Polaris and imagine the movement of Spaceship Earth, rotating on its axis, always pointing at the pole star. But that's not quite true. Over 26,000 years, it draws a circle. Imagine the Earth's axis jutting out of the North Pole, stretching to infinity. It meets the pole star. From one millennium to another, other stars become our northern star. 12,000 years ago, for the cavemen, it was Vega. 5,000 years ago, Thuban. That's when the Egyptians built the pyramids. They aimed a shaft north, and what they saw at the end of that shaft was the star Thuban. Just to the left of the Great Bear, the Big Dipper, while today, tourists see the pole star. Thuban pole star. This is the angle the Earth has swung through in 5,000 years. We can all imagine months and years, perhaps even a century, but to imagine 5,000 years, you have to look at the angle between Thuban and pole star. As we travel on our orbit, we see the stars move slightly from one week to the next. Constellation of Orion, easily found to the south. With its head, 2 arms, 2 feet, and belt. The slight daily shift of the stars is completely lost in the enormous sweeping motion of the Earth's rotation, changing our field of vision every hour, making it revolve from night to day and back to night. Look at Orion every night at the same time. You'll see the celestial sphere rotating at a snail's pace. Of course, the celestial sphere doesn't exist. It's an imaginary dome where the infinitely distant stars seem to sparkle. And of course, the celestial sphere doesn't turn. It's us on Earth who travel around the sun once a year, 360 degrees in 365 days, 1 degree a day. So every day at the same time, we look 1 degree left and see that the stars have drifted 1 degree to the right. This week at around 9 p.m., Orion is due south. In 2 weeks, it'll have slipped a little to the right, and in a month, a little further. The stars move 1 degree every day, and each day they pass 4 minutes earlier. 1 degree in space, 4 minutes in time. Space and time meet. Since the beginning of this cruise, we've stressed the difference between the planets nearby and the faraway stars. But there's one star smack in the middle of our planetary backyard: the sun. Yes, the sun is a star. All those twinkling dots beyond the planets are stars, distant suns. Galaxies are billions of suns. Seen from the Earth, the planets look like stars, but you only have to look at the sun to be dazzled by the difference. The sun shines, while the planets only reflect a part of the sun's light. The sun sends us light and heat, a gigantic nuclear reactor. In fact, the solar system is the sun, and next to nothing. All the planets, Earth included, make up only 1,000th of the solar system. The sun is too big for us to grasp. The entire Earth-Moon system, including the Moon's orbit, would fit inside the sun. Yet this enormous sun is a relatively small star. And if we compare our sun to other stars, our little Earth disappears completely from the screen. In the constellation of Orion, Betelgeuse is the largest star we know. It's so big it could easily swallow our sun along with the Earth in orbit. All that would fit inside this star. We're familiar with the dimensions of the infinitely small, atoms with the nuclei and spinning electrons. We also know the dimensions of the infinitely large, the universe and the stars. Now there's a new dimension, our solar system. We are the first generation who can grasp and explore it. Our journey's aim is to let you experience this new dimension.